Lihong Cao is a director in the ASE group responsible for new packaging, technology development, working on all the things that we've been talking about, 2.5D, 3D, fan-out wafer level packaging, and on, and works on technology promotion and program management and engaging with their customers. She has worked on many things to enable high performance computing and artificial intelligence and machine learning. So welcome, Lihong.
Yeah, thank you, Era. And hello, everyone. Today, I'm going to talk about advanced packaging design platform for chiplets and heterogeneous integration. Here is the outline for today's talk. So first, I will start with the motivation and talk about the semiconductor technology scaling trend and the demands for chiplets integration. Then I will introduce advanced packaging technology platforms. And subsequently, I will talk about the ASE design platform for chiplets and heterogeneous integration, and discuss the package design case, as well the electrical performance validation. And finally, I will conduct the summary. So we have seen the digital transformation has encompassed multiple sectors in our daily life, from Internet of Things to Internet of Everything, automotive, industrial, 5G, AI, machine learning, and data center. It has driven the semiconductor industry growth significantly. Based on Prismark report, in 2024, mobile, PC, computing, server, and communication infrastructure are still the key drivers to dominate the semiconductor industry. Especially, the strongest growth will be from server, storage, and communication infrastructure, with a CAGR about 8.1% growth, and automotive with a CAGR of 7.1% growth from 2019 to 2024. If we look at further on semiconductor technology scaling trend and the performance requirement, first, the number of transistors continue increasing and the silicon node becomes smaller due to the high performance demands. However, if we look at the graph on the left, the total cost of wafer development with a very smaller silicon nodes has increased significantly. You also heard this from Thomas' talks just now. Meanwhile, the performance requirement has increased as people are looking for more cores in their computing engines. The graph on the right shows the I/O bandwidth are doubling every 3 years. Therefore, as a result of these diverging phenomena, there are urgent needs of new technology innovation. So chiplets and heterogeneous integration has become the key enablers. The multiple chiplets and heterogeneous integration allow disaggregation of SoC from monolithic SoC to modularized SoC, by partitioning to mix and match different silicon nodes, to reuse IP, to allow system having more flexibilities and optimize the performance, such reduce the cost in overall. And also, most importantly, it shortened the time to the market. So chiplets and heterogeneous integration have driven the advanced packaging development, and new breakthroughs have been achieved. So now I will move to the second part of my today's talk, advanced packaging technology. So the advanced 2.5D silicon TSV interposer packaging technology have been used to integrate multiple chips for HPC application in mass production in the market. So there are 3 waves. If we look at the 2.5D silicon interposer packaging technology history. So the first wave is from the 2007 to 2010, which was mainly for MEMS, RF, and the sensor application with low I/O accounts. So the second wave was from 2011 to 2014, with Xilinx announced FPGA integrated with the stack structures, and the memory suppliers like Samsung and SK Hynix develop the DRAM stack applications. The third waveform was from 2015 until right now, mainly for high-performance applications after AMD first time introduced the GPU physics stack HBM in 2015, following by many IDMs, companies like NVIDIA and Broadcom. With the demands of AI machine learning and HPC, the interposer size has been increased significantly. High cost is the key concern for 2.5D silicon TSV packaging technology. So due to the cost concern for 2.5D silicon TSV technology, the alternative packaging technology, such as TSV-less or organic RDL solutions, have been developed during the past few years. Below chart lists the major alternative advanced packaging technology, such as Intel EMIB, SPIL, ASE, M-Core, and TSMC Fanout RDL interposer, as well as 3D copper-to-copper hybrid bonding have been developed. In ASE, we have provided advanced packaging platform with a wide portfolio from FCBGA with low to medium I/O account, and also the substrate, the copper interconnect line spacing from 35 by 35 micron down to currently 12 by 9 micron, to high I/O interconnect density called 2.1D, or people call 2.xD. The fan-out on substrate and the fan-out embedded silicon bridge to higher I/O density 2.5D silicon TSV, and with copper RDL trace line spacing from 2 by 2 micron down to 0.4 and 0.4 micron, to super high I/O interconnect density of a 3D hybrid bonding. The advanced packaging technology can fulfill the substrate gap for high-density chiplets integration. Compared to conventional package design, the advanced packaging design for chiplets integration has converted from sole package design to hybrid IC packaging design due to the RDL interposer and the 2.5D silicon interposer interconnection between the silicon chip to the substrate. So here, I will focus on the hybrid design for advanced packaging for chiplets integration. So now I move to the discussion of our ASE design platform. In ASE, we have provided advanced packaging design case called the PDK instead of ADK. People call the OSAT usually called the assembling design case, with mainly focusing on DRC, design rule check over design for manufacturing. Here shows an example of key contents in our PDK. It will start from the structure material analysis, such as RDL stack up requirement, material stack up, and the properties. Then we will go to do the pre-analysis, including the floor plan, warpage, and the electrical simulations. Subsequently, we will look into die-to-die design, which is very critical for chiplets integration. In this session, we will do the RLC evaluation, electrical root deck check, as well as stress simulation. Another key component in design is the SerDes design, also become very important for the high-speed signal transmission. In SerDes design, we will do the insertion return loss, crosstalk evaluation, and the power domain networking design. We also need to consider DRC performance per element, as well the electron migrations. And finally, we will do the sign-off of DRC LVS check based on the standard design requirement. Here, just to show the one example of our high-density focused hybrid design flow. For the substrate design, we will use the conventional package design tool to yield Gerber file. For Fanout RDL design, we will use the IC design tool to do the auto router And then we will use the same package design to optimize the RDL design and yield the DDS file for DRC and LVS validation. Finally, we use auto mask design to generate the RDL mask for manufacturing process. In our hybrid design flow, the RDL routing, design rule deck checking, and LVS as mask generation can be done automatically. Design cycle time is very critical, and it will take a few weeks for chipless integration design due to the complexity. Several speakers had mentioned in their talks. Here shows the one example by using an IC design tool called Auto Router. When we receive the net list of relative coordinates, if we go through the conventional package design tool to make the RDL routing, it will take a few weeks. But by using the Auto Router IC design tool, it can produce the similar RDL routing structure, but the total layout design cycle time can be reduced to 50%. Meanwhile, the Auto Router not only can be used for die-to-die design, but also can be used for micro bump and CFO bump for fan-out chip-on-substrate design. In our hybrid design, after we complete the RDL design, we also create the auto mask generator to design the RDL mask. The design lead time can be reduced from 3 days to 1 hour. Most importantly, the auto mask generator also can arrange the non-good die locations to maximize the die per wafer quantity for yield improvement. So this is very important for larger fan-out die size per wafer. Here, we just showed our view of our advanced packaging hybrid design flow. It can be used for homogeneous design as well as heterogeneous design. Here shows the two design examples for homogeneous 2ASIC fan-out design with 4 RDL layers, and the line spacing is 2 by 2 micron, as well the heterogeneous integration of 1 ASIC with 2 HBM and 4 RDL layers, and the line spacing 2 by 2 is called high density fan-out design. Signal integrity and the power domain network play very important role in chipless design. There are many different die-to-die interconnects through different packaging solutions, such as serial I/O connections like ultra-short reach, SerDes, and the parallel I/O interconnection, such as bounce of wire, open HBI, and UCIe. Optimization of SI and PI have to be done in chipless design. Among this, the critical I/O design verification, such as die-to-die, and the differential pairs of SerDes have to be evaluated. Here shows 2 examples for design optimization of SI for die-to-die connections for fan-out chip-on-substrate and 2.5D silicon TSV. After design optimization, both FOCOS and 2.5D die-to-die connections can meet the spec requirement. Same results was also observed for 28 gigabits per second SerDes design by using our hybrid design tool. So the power integrity is also very critical. Here shows an example after our design optimization. The PI performance for dynamic power noise level meets the system specification for both fan-out FOCOS and 2.5D silicon TSV. So you may hear from previous speakers talking about the design challenges for chipless integration due to the complexity requirement. From all sides perspective, we are facing the same challenges. Here, just highlighted some of the key drivers and the design challenge. The driver 1 is a high-density scaling demands, such as smaller silicon node from 7 nanometer down to 5 nanometer, even 3 nanometer, and a smaller pitch for high-density connections. There is a need for a co-design tool to bridge silicon, packaging, and the board seamlessly. The driver 2 is manufacturing feasibility to control the package warpage and the coplanarity to provide a good reliability and high yield. It requires a new DRC, LVS, and electrical code simulations. So the driver 3 is the high performance and die-to-die interconnect standardization requirement. Last but not least is the collaboration among the chip designers, packaging manufacturers, and the system integrators to build up design ecosystem. I think this is my last slide. So finally, I will summarize the conclusion of today's presentation. The chiplets and heterogeneous integration optimize the performance and the cost. Advanced packaging offers solutions for chiplets and heterogeneous integration. ASE has provided advanced packaging solutions and a design kits for chiplets integration. The system co-design and the collaborations are needed to build up design ecosystem for chiplets and heterogeneous integration. I think that's the end of my presentation. Thank you. Thank you for your attention. Thank you.
Thank you, Lihong. I have questions, but let's see if the audience has some. Let's start with a high-level question. You know, in the world of co-design, you know, roughly what percentage of customers come in and say, this is the exact advanced packaging we want, or what group come, you know, what's the relative proportion of customers who come in and say, well, here's sort of what we want to do, which packaging do you suggest? And then you have to then help with all the modeling and the analysis to figure out the packaging. I mean, is there, you know, is it 50-50, or do you spend more time trying to help most of your customers figure out what type of packaging to use?
Yeah, that is a very good question. And nowadays, and you see before is the design over, you know, the solutions is provided by the IDM, you know, for example, and over by the system integrators. But now we see more and more. If you look at the percentage, I can see, you know, from kind of a 70 to 80%. And the people will go for us to ask the advanced packaging. And also with kind of the technology, what I introduced here, several packaging technology, they have different sweet spots. So we have to, based on the design requirement and to provide suggestions. So this is the one, so 70 to 80%. But we are not stopped here. For example, the RDL design, you know, the intermediate design, we see the conversion. We see, you know, the IDM going down to us, and also, you know, the foundry going down to us. Same time, so we're going up, you know, for the IC design type of solutions right now. So yeah, so we need to collaborations, and we have provide, for example, the intermediate, the 2.5D silicon interposer design, the FOCOS, the Fanout organic interposer design. So I see more and more collaborations, and the percentage and become more and more. And we will see, you know, eventually maybe you cannot separate the side, you know, 10%, you know, this is from all sides, and this is 90% from IDM. Yes, we see the trend, the conversion trend. Yeah.
And then so this means you also have to engage much earlier to, you know, get involved with like what Thomas was talking about, you know, channel analysis and jitter, and because the packaging changes the margins that they have in their design, and so you've got to be even closer to your customers from the beginning, it sounds like.
Yes. So we have several cases study, and we engage at the earlier design scoping stage. It's not like it's scoping. So we have more and more collaborations at the design scoping stage. Yes.
Understood. Some particular questions. You talked about using the wafer map in the auto mask process. So do you generate custom RDLs for each wafer map, or what was, could you clarify that a little bit?
Yes, definitely, yes. So, okay, so we talk about the RDL mask because we are the manufacturing. So eventually we will make the RDL. So there are two sources, generated the RDL mask. So from design, so we also can generate it from design to the real, RDL mask. So this is one. Another one, we also, receive, if IDM can do the mask design, but we need to do the DRC check. We need to eventually, we will use the auto, mask generator to generate the physical mask design. So we do the mask design, the generations, yes. So that's why, but the source, either we do by ourselves design or we receive the design, but we have to generate it by ourselves. Yeah.
I understand the generation, but I thought you said you use the wafer map, i.e. the yield map of a particular wafer, or did you just mean the map of the entire wafer, the masks, the reticles?
Yes, we map the reticle because we do the reconstitution. It's not directly from wafer, it's the recon wafer, and we need to generate the mask. That's how we can place, select the locations for the Fanout, for the Fanout wafer, or you do the 2.5D recon wafer, we call the non-good die. We put the non-good die on our recon wafer. Yes.
Okay. Understood. Okay, and then a question came in. Do you find the requirements for package designs are better defined now than, let's say, in the past, 10 years ago? I mean, are there more requirements, that the customers come in, or is it still not as well defined as you would like?
Yeah, it's not really defined. I can say that because you look at the package design requirement and more complicated. And we have, in our ASE, we have like thousands of customers, and each one have a different, the package format. But we haven't seen, how to standardize to package, and also package requirement. So that is another gap and another challenge. We try to bring together, to build up an ecosystem. That is a very challenging, yes.
Right. And so you probably have a very long checklist of questions that you need to have the customer specify what they want, or which ones are don't cares and which ones are things that they need a specific thing that they haven't either specified or haven't thought about yet. So
yes, the list and become longer and longer because the advanced packaging is not like before is simple, but you have to consider, the intermediate, the organ in the powder, how to make connections, and that has become more and more complex.
Right. Okay. And one last detailed question. You talked about for the RDL, you generate GDS2, and for the laminates, you have to do Gerber. Do you actually have a tool that will do netlist extraction across both domains, i.e. where will one tool read the GDS2 and the Gerber in, or does your process stitch them together? Because, one of the things that we often see is people want one tool, but I've not in the past found a tool that does both. You have to convert one to the other, or you have to stitch it together later. But now that you have this in advanced packaging, or do the laminate companies now take GDS2? So do you have a process for this to make sure that your netlist extraction is correct?
Actually, yeah, absolutely. The one you described, and also, yesterday's people talk about, the ecosystem. So like you said, we don't have the one system can do, you know, the Gerber Fanout and the GDS Fanout and, you know, and integrated together. So theoretically you can do it, but practically, and it's very time consuming. And also they have, you know, you have a lot of connections. You have to make the root deck check. That is very difficult, yes. So the fast way we can, you know, we can do partially. For example, I mentioned about the auto router. So we integrated, you know, partially the IC design tool in the package design, inside, you know, the packaging design tool. We can combine, you know, the DDIS file and the Gerber's file, you know, kind of we do 50 to 70% work, but still not 100% to integrate it together. So yeah, so that is one. We hope the EDA, you know, the two suppliers, and can develop something can useful, very friendly, and also cycle design time. Yes.
Or I'll put a call out to laminate suppliers. They should just learn how to use GDS too. I mean, it's, you know, or it's just this bifurcation. We have this at the system world too. I mean, you have the chip designs in GDS too, and you know, substrate, you know, silicon substrate, and then the printed circuit board people are all still using Gerber, and it's just this weird boundary that just has existed for years, and nobody wants to cross it. So we'll put a call to action out there for that one. So, but thank you for highlighting that. Okay, I thank you very much for an excellent presentation. So thank you, Lihong. And once again, I'd like to thank our sponsors, Advantest and ASE. Advantest has received the highest ratings in customer satisfaction, the VLSI research survey for the last 2 consecutive years. So congratulations to them. And ASE supporting the chiplet era, which has begun in terms of providing advanced packaging and working with their customers like Lihong has discussed to do heterogeneous integration and advanced packaging. So thank you both to Advantest and ASE who've made this webinar possible. I also would like to thank all the presenters, and most importantly, thank you for joining us today. I look forward to seeing you all tomorrow. Thank you.